In this video, I'm going to introduce the multiple linear regression model, which extends simple linear regression from the previous chapter to multiple predictor variables. And to motivate this model, we're going to look at a fairly simple example where we just have two predictors, because then we're still able to see everything that's going on. So just as in simple linear regression, it's important to set up your variables to start with, so you're very clear on which variable is which. So just as in simple linear regression, we have a single response variable, which we'll call y, and this is going to be quantitative, and sometimes it's called a dependent variable or an outcome variable or an output variable. And then now we have multiple quantitative predictor variables, x1, x2, x3, and so on. And these are sometimes called independent or input variables or covariates. So the example that we're going to run with for this video and subsequent videos is data on student final exam scores. And so that's the response variable y, and that's going to be measured out of 100. And then we're going to have two predictor variables. x1 is going to measure the time spent partying during the last week of term in hours, and x2 is going to measure the average time spent studying during the term in hours per week. So for this particular application, we might be interested in how much we expect the final exam score to change when we change the values of x1 and or x2. Or another kind of question we might be interested in answering is, what do we expect the final exam score to be when a student spends 7.5 hours partying during the last week of term, but an average of 1.3 hours a week studying during the term. So let's set up some notation so that we can analyze this situation. So to illustrate, let's suppose that we have this relationship between exam scores and time spent partying and time spent studying, such that exam score is on average 70 minus 1.6 times the party hours plus 2.0 times the study hours. So we can put that in this equation where expected value of y given x1 and x2 means the expected exam score given certain values for x1 party hours and x2 study hours. And the equation that we're going to work with is 70 minus 1.6 x1 plus 2.0 x2. The I in these equations is just keeping track of students. So I runs from 1 to n, the sample size. So this is what exam scores are on average based on partying hours and study hours. But individual student exam scores will deviate from this expected amount, and they deviate by an amount which, just as in simple linear regression, is represented by the letter E, and it's called the random error. So we can express y, which is the actual individual exam score for someone, as determined by x1 and x2. So that's given by the formula for the expected exam score, so 70 minus 1.6 times x1 plus 2.0 times x2, and then we've got a random error E. And that error represents variation in exam scores due to things other than x1 and x2 that we haven't measured and haven't put into the model. So this might be underlying quantitative skills, abilities, taking exams, other things that we haven't actually measured. So as a concrete example, let's go back to that student we mentioned in the last slide. So the one that spent 7.5 hours partying in the last week of term and only spent 1.3 hours a week studying the rest of the term. What would we expect their exam score to be? So we plug in the values into the equation. So 70 minus 1.6 times 7.5 plus 2.0 times 1.3, and we get 60.6. So that's what we expect this student to score based on this relationship here. But it might turn out that this student is actually quite strong. Maybe he or she has got good quantitative skills, and despite not studying very much during the term, they were able to actually pull off a 65% on the final exam. So if we do the calculation, we can figure out what their random error is. 65 minus 60.6 is 4.4. So they got an extra 4.4% from factors that we didn't measure in the model. So we can illustrate this model when we have a multiple linear regression model with just two predictors in a three-dimensional scatter plot. So that's what's here, and we can think of the two predictors as being on these two axes here. So this one, party, is x1. This is the time spent partying in the last week of term. And then this one coming out this way is the average time spent studying per week during the term. So these are the two predictor axes. And then the response axis is straight up. So the higher the exam score, the higher up the scatter plot the point will be. So the points are the filled circles. So I've got 5 of them in this diagram. And these are in three-dimensional space. And then this flat grid, this is the regression plane. So in simple linear regression we had a regression line. In multiple linear regression with two predictors we have a plane, because that equation here, this is geometrically represented as a plane in 3 dimensions. So the open circles are positioned on that regression plane, and those are the fitted values according to the model. So for each observed value, let's focus on this one here, say. The observed exam score for this student is represented by the filled-in circle, and where we predict them to be is the open circle on the plane. So this particular student did worse than we expected them to. Their exam score is lower, it's below the plane. Whereas this one over here, this student did better than we expected. So actually looking at it, I think this is the student that we were just talking about. So the one with 7.5 hours partying and 1.3 hours studying. So if I go out 7.5 hours on this axis and 1.3 hours on this axis, I would get to this point here, and then this is their observed exam score. It was, what did we say it was, 65? But the point on the plane, on the fitted regression plane, is only 60.6. And so they had a random error of 4.4. So their error is positive, and they did better than expected. So here's our multiple linear regression equation in general. So when we have multiple predictors, so not necessarily just two as in this example, but multiple predictors. So we represent it using this formula here. Expected value of y given x1, x2, and so on is b0 plus b1 x1 plus b2 x2 plus 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 plus. And the interpretation of the parameters here, b0 and b1 and b2, b0 would be the expected y value when all the x's are 0, because if all the x's were 0 in this equation, this part of the equation would go away and we'd be left with expected value of y given all the x's is b0. b1, I was saying, is the slope in the x1 direction. So in other words, when we hold all the other predictors constant, the number b1 in front of the x1 predictor tells us the slope in the x1 direction. So what does that mean? Let's go back to our picture to see what it might mean in this case. So x1 in this case was part E. So if we fix study, so let's fix it down here, say. Okay. And then if we're fixing study at this point here, and then looking at what happens to exam scores as part E increases, it's going to be along this line here, this grid line here. Okay, and this is that slope in the x1 direction. According to our equation, that slope is minus 1.6. Okay, so it's negative, it's going down. If we fix study at the second point here, we would be tracing this line here. Same slope, minus 1.6. Or fix study at this point, and we trace this line. Okay, it doesn't matter where we fix study, the slope in the x1 direction is always the same, it's always negative 1.6. Similarly, plus 2.0 is the slope in the x2 direction, holding x1 fixed. So let's hold part E fixed, say at this value, and then look at what happens to exam scores as study increases. We're going to be tracing along this line here. And that slope in the x2 direction is 2. Fix part E at this value here, and we'll be tracing this line. Same slope, plus 2, and so on. Okay, so those are the interpretations of the regression parameters. We hold all the other x's fixed, and the parameter tells us the slope in that predictor's direction, holding everything else fixed or constant. So this is the population multiple linear regression equation. That brings us to the usual statistical question, is how do we estimate that equation? So right now these are unknown numbers, b0 and b1 and b2. How do we estimate those? So in other words, how do we derive this sample equation? Y hat equals b0 hat plus b1 hat x1 plus b2 hat x2 and so on. How do we estimate these parameters? So the way that we estimate them is using least squares, just as we did with simple linear regression, and we'll talk about that in the next video.